Yeah, and that's why. Thank you, John. Why we're going to create this a kind of a follow-up video, because if our listeners and viewers had a chance to listen, it was really a good a contrast to what you often hear in the news, which is a lot of different controversial issues. But you were helping us try to understand the science of it, and that was really helpful, especially with the idea that there it seems like there was a previous method of trying to develop vaccines, and uh, this newer method related to RNA. Do you see this as a dramatic change in how we're going to treat viruses in the next 100 years?
This is going to revolutionize medicine. But again, it all has to do with genes and understanding what genes are responsible for what product, or what genes are responsible for things. Once we understand the genes and the sequence, we can take the parts of the virus that aren't dangerous or that aren't lethal and use them against the virus itself. So imagine now if we sequence breast cancer cells. So once we sequence breast cancer cells, we will know what parts of the breast cancer cells are responsible for the membrane, what's responsible for the messenger RNA, what's responsible for the spike proteins that allow it to bind. Once we understand that, we can go through the same process that we did here and eliminate breast cancer.
And they're doing those studies now.
And
There's some studies where they're even taking tissue from the patient, from the cancer, sending it off to the lab, changing it, sending it back in so that then it attacks the rest of the cancer cells.
And you're actually using your own body to fight
Yeah,
off the cancer
cool.
cells with that. Yeah.
It's like science
You're-
fiction.
yeah, you're just giving the body instructions on how to kill the virus or
Yeah.
how to breast cancer.
You
You're
know-
not giving the body the virus, okay? Or you're not giving the body anything dangerous. You're giving the body the instructions, essentially the code on how to kill either cancers, how to kill other viruses. I mean, the common cold, anything we can sequence, anything that we can sequence the genes, we can understand how to either use it to our benefit or use it to help the body render it inactive.
One of the things is that some of the vaccines, the new vaccines require two vaccinations. If you get one vaccination, it kind of sets off your body to be able to aware of how to deal with this. And what's the second one do?
Again, a lot of times you have to give the body enough instructions to do it. So you can, here's the thing, we can give instructions to the body on how to kill the virus and also include instructions in there on replicating, meaning reproducing. If you do that, okay, you're then able to not only kill the virus, but reproduce cells that kill the virus. Okay, so the first shot kind of gives you just enough instructions on how to make it, and the next one really is the one that takes it to reproduce. Okay, so first you get the instructions. All right, this is how you kill it. This sequence. Now that sequence has to be repeated billions of times. Okay, the second shot allows the reproducibility to reach the amount that is needed to kill the virus.
Now with the Johnson & Johnson, it's just, and the AstraZeneca probably will just be one injection. Is that because that method is different, it doesn't require the follow-up?
Most likely, the Pfizer and Moderna vaccine will work after one. Okay. Again, running mathematical models and understanding the sequence, you can predict with fairly good outcome that it will be able to be one shot, may be able to elicit enough immune response that your body can be. It just was developed with 2 shots. Again, the same reason it was developed because of time. It was the same reason it was developed at minus 86 degrees. Minus 86 degrees kind of happens to be when the molecules don't react with one another. So if you keep it at that temperature, you know that they won't react. So once you raise the temperature, you raise the ability of the molecule to react in a ways that you don't understand. So you need to have studies on how it is at room temperature or how it is in a refrigerator. Those studies take time. They take 6 months or a year. So in order to cut off another 6 months or a year of time for development, we developed the virus at a very cold temperature and just released it then. Okay, we didn't take the time to reorganize this sequence in a way to make it viable at room temperature. We know what molecules to change, okay? It would take time to change it, to build it, and then to test it. All the time that we needed to save in order to stop the mutations from occurring quickly.
Are they actually making the vaccine at the plant where you work?
No, they have a pilot plant there, okay, which means that's the first vaccine. So it's actually being reproduced in Andover and in different sites, but they developed the vaccine there, and the first vaccine was made there, and that was given to the big plants that can make it on a large scale.
Now, I expect that those plants are probably at maximum capacity.
They are. They've been at maximum capacity for about a year. But again, the difference between the Pfizer Moderna ones is that the versus Johnson & Johnson, the Johnson & Johnson, it takes about, like you said, 60 to 90 days to actually grow enough cells to make a vaccine. Okay, they have these huge tanks that are big as buildings that they grow these cells in. They feed them. It's very, very precise, very, very particular. And if one process isn't followed correctly, all of it is no good.
Yeah.
again, a little different than taking the sequence and just adding the other half to it.
Yeah, yeah.
So easy,
thank-
isn't it?
yeah. Well, thank you, John. I want to stop us here on this segment because this was really about the kind of the production and comparing and some of the more of the technology. Let's stop here one more time and then we'll pick it up with one other subject.